Today we'll be discussing about the alternative forms of the pull-ups. So the name alternative forms of the pull-up says that if you are going to use a different kind of transistors in the pull-up network. First of all, we'll see what is a pull-up network and what is a pull-down network. Now, if you see this circuit, whenever a complementary metal oxide semiconductor circuit, if you see there, it will be having two parts. One is the pull-up network, the other is a pull-down network. So our concept, today's concept says that alternative forms of pull-ups means if you are replacing the pull-up network with a different transistors, what the characteristics will be, how the output will change, and whether it is going to affect the output or not. That is what is our topic today. Now let us proceed with first one, that is a load resistor. So now if you see the arrangement here, in pull down network we are having the NMOS, and in the pull up network wherever we need to have a PMOS we are using a load resistor. So this arrangement will give the CMOS inverter output, but this is not widely used because of the large space requirement of resistors produced in a silicon substrate. So the problem with having a load resistor in the pull-up network is that it is not that much easy to fabricate, and it takes more space for fabricating on a silicon substrate. So the next model what we have here is the NMOS depletion mode transistor pull-up. That means in my CMOS inverter, in the pull-up part, wherever I have my PMOS, there I am going to use a depletion mode transistor. If I use a depletion mode NMOS transistor, then how your characteristics are going to affect, that is what we are going to see. So this arrangement is having one NMOS transistor and one NMOS enhancement mode transistor, and the other is NMOS depletion mode transistor. So what is in this settings, or in this inverter, what we have observed is dissipation is high since rail to rail current flows when Vin is equals to logic 1. So when my input is equals to logic 1, that is when V input is high, this NMOS is acting as a closed switch, and even the depletion mode transistor acts as a closed switch. So what is happening is there is the current which is flowing from your VDD to ground. So switching the output from 1 to 0 begins when Vin exceeds Vt. So if you observe the graph here, so what is happening is whenever the output when it starts switching begins to 0 means when my input is equals to 1, it spontaneously it will not give a output 0, but when my input is crossing the threshold voltage, at that time the output is becoming 0, but according to my graph it is showing that the output is a non-zero. So when the switching the output from 1 to 0, the pull-up device is non-saturated initially, and this presents lower resistance through which a charge to charge the capacitive load. So always what is that, my pull-up network is in the non-saturated region, and as it is in the non-saturated region, a little bit of charge will be present in your capacitive load, and it will never make my output to become 0. So the current flows in the circuit when it is crossing the input voltage is crossing the threshold voltage, and as my depletion mode transistor is in the non-saturation region, the output never becomes 0. Now let us see if I replace the pull-up network with an NMOS enhancement mode transistor. So in NMOS enhancement mode as a pull-up, the CMOS inverter, it will be having two NMOS transistors which are connected in series. This important feature of this arrangement. Now dissipation is high since the current flowing when Vin is equals to logic 1. That is what we have seen in the previous case also when we have used the depletion mode as a transistor. Now Vout can never reach VDD if VGG is equals to VDD, and is normally the case. So Vout never reaches VDD when logic 1, that is VDD, if VGG is equals to VDD, as it is the normal case. Why it is not going to reach the maximum value means some of the voltage which will be used here to form the channel. So VGG may be derived from a switching source, for example one phase of the clock, so that the dissipation can be greatly reduced. If you are deriving it from a switching source, then we can greatly reduce that one. If VGG is higher than VDD, then extra supply rail is required. Now, what is that? The VGG whatever we are providing, if that is greater than your VDD, one more power supply line we need to give it to your pull-up enhancement mode. So that's why whenever I use an NMOS enhancement mode in the pull-up network, there the output is never reaching the value of the maximum value. It will be down by a value of VT1, and even when my input is maximum, the output is always a non-zero and it is never becoming a zero. Now complementary transistor pull-up CMOS, as even we have seen this one in my previous case also. No current flows either for logic 0 or for logic 1 input, that is it is having the maximum values. So full logic 1 and 0 levels are present at the output side. So whenever I am giving input as 0, it is presenting a maximum value, and when input is 1, it is presenting a minimum value. That's why we have seen the different regions of operation of CMOS inverter in 5 regions: region 1, region 2, 3, 4 and 5. In first region already we have said that the input is equal 0, P will be on and N will be off, and in region 5 it is quite opposite, N will be on and P will be off. And when the input voltage is slightly greater than your threshold voltage, both the transistors will be in on condition, but N will operate in the saturation and P will operate in a non-saturated region. And again the quite opposite is your region 4, and maximum gain will be attained when it is reaching the middle value, means when both PMOS and NMOS transistors are in saturation, then maximum gain will be there. So the current flowing in both the channels will be equal. So for devices of similar dimensions, the P channel is slower than the N channel device. So if now what are the different types of alternative forms we have seen here means, the first one what we have in the pull-up part, that is if you are using a resistor as a load. Second one is if you are using a depletion mode transistor and a depletion mode NMOS transistor in the pull-up network, what are the features? And if you are using an enhancement mode NMOS transistor in the pull-up, what are the characteristics of your CMOS inverter? And if you are using a PMOS inverter, what are the characteristics? That is what we have seen today in our video. Thank you. For more videos, subscribe to our channel KK Lectures. Thank you very much.